Well, good morning, everybody. I hope you digest your pizza from yesterday. It was a little bit much for me, but so today we have our fourth lecture. Actually, it's a little bit confusing. If you count my contributions, then it's 4 lectures, but Manuel's got now also in series, so this is now the 5th lecture in total. So on the wiki, you will have a little bit of confusion about these two, but you know what to do. So today we will be talking about the recoil separator SECAR, specifically designed for FRIC in more detail. Of course, you have already operated COSI with SECAR and heard about it. But let's get a more detailed view of what we have done there and what the status is and what you need to know if you want to work with SECAR. In the last lecture, so it's 3, but in total it's lecture number 4, we have learned about 0 degree. Of course, all recoil separators, fragment separators, and nowadays most spectrometers work because there's the physics at 0 degree. Spectrometers many years ago measured many angular distributions, so at backward angles, 0 degree was a new development for new physics with spectrometers. So we have learned a lot about the techniques that are needed for 0 degree separating by B-row or by mass in the case of the mass or recoil separator. Inverse kinematics is helping for the background in the case of St. George, who operates with stable beams, but for radioactive beams in the P-gamma reaction, you need the inverse kinematics, otherwise it's not even possible to make this reaction. Recoil separators, you got an overview. Of course, we are focused here on the recoil separators close by. St. George, you heard yesterday, stable isotopes, alpha gamma, and today, unstable isotopes, SECAR. SECAR is designed for the full RP process up to 65. Of course, there's no hard limit there. It's not specifically designed for that, so there may be limitations if you do experiments there, but in principle, they are also possible. Now, you have seen this slide. If you ever design an instrument and you are the person who works on the ion optics, what you need initially, you need to know what the physics goals are. And the physics goals are here represented by a list of reactions. That may not be so simple in all cases. There may be very different types of experiment, like for the HRS, they have to be accommodated. Important for you is that you're not designing something for physics goals, but ion optics parameters. So you need to negotiate and adjust to what the physics question is, ion optical parameters, so that the instrument is doing that, what the physics goals are. That is very important. So that we have done here, and you know already that we extracted the maximum B-row, the acceptance, the angular acceptance, and here's a complete list what the design parameters, we call it, have to fulfill. So now you can focus on building a system or commissioning it, adjusting it to fulfill these specific requirements without having to worry about if this or that experiment is possible. These are so defined that all the experiments of the physics goals are possible. Requirements are met. So the transmission 100% comes from the fact that we have very low cross sections, particularly at low energies. So if you don't have 100%, maybe 95 would be good, but if you lose half of that and you have anyhow only every 15 minutes an event, then you have every 35 minutes an event, and that experiment may not be possible. So 100% transmission, the experiment has to do. The minimum and the maximum rigidity for B row and E row is written here, and they reflect the range of energies that you want to do. In case of SECAR, it's very small energies. So these are relatively small, low field requirements. The acceptance not only covers the minimum that you need for the, if you calculate the kinematics, and you have done that, it would probably be something like 16, but there's some extra space for blow up of the emittance in the target. So in reality, after you make simulations, not only the kinematics, you may need more in order to avoid that you lose particles and you don't meet your 100%. Energy acceptance is similar, plus minus 3.1%. The also reflects what is needed. The rejection of the separator, beam rejection, is 10 to minus 13. So for 10 to the minus 13 beam, which you want to destroy, there should be only one event coming through your system. Of course, 100% of the recoils. So that is the definition. And this is driven by the mass separation in the recoil separator. So we have to find a link between the mass separation and this beam rejection. And that is a difficult thing, and I will talk about that in an upcoming slide. The detector system, once we have done that, the detector system should be able to count everything that comes through, and it's not all the good recoil particles you want, but it's also leaky beam, scattering from residual gas, and all possible background sources. So the detector does an additional 10 to minus 4. So now the mass resolution. We talked about earlier about the momentum resolving power. It is the dispersion, momentum dispersion divided by magnification and divided by the full target size. So we typically think about it as a millimeter, but that depends, of course, on the particular beam. The mass separation is defined similarly, but with COSE you know now how to calculate the matrix element M17 or X delta M. So you replace the momentum by the dispersion by the mass separation. And then you have the mass resolving power. This is for the momentum dispersion, the resolving power, this is a first order quantity. So this is the potential of the X instrument which you get if you don't have any other interferences like the higher orders. And you will see SECAR will be limited by the higher orders, and these can actually be calculated as you have done in your hands-on sessions. The resolution, as opposed to the possibly best resolution, resolving power, is d over dispersion divided by the magnification times the target thickness, which is the size of the image. X0 is at the target, magnification is what the system does, so this is the size at the image. Now, the size of the image has higher orders, unavoidably. You correct them as good as you can, but there's a limit, and we calculate that and specify that. So the X higher order for the resolution that you want to calculate, and what ultimately you should be getting with a real instrument, is magnification times the full target size plus the higher orders. So how do we find the resolution, or how do we find the X0, including the higher orders? So we have to make higher order calculations, and we have to simulate the emittance of the beam by many rays. So ideally, you would have here many rays, but then you cannot calculate COSY, cannot fit, cannot optimize it. So we found out that about 189 rays are about enough to characterize a system, including the higher orders. So we run 189 rays spread over the emittance of the beam and calculate then the size as you have done in your exercise for the emittance measurement. So that's all, you know already the techniques how to do this. And the emittance is given by, of course, the acceptances, but then this includes extreme rays like a rectangular emittance here, and the corners you actually don't see. There are no events, so I limit the acceptance in angle, in energy, acceptance horizontally, vertically, and in energy, and sometimes I do without the energy, smaller than 1, limits it, like in this cartoon here, to the ellipsoid, not the full rectangle, because this is a big angle. The higher orders quickly increase. You don't want to include those. They are not practical. So these 189 rays. So with this rays, the higher orders were calculated, as you know by now how that is done, and optimized. Now, we don't believe that these are really describing everything well. So Manuel in particular did Monte Carlo simulations. I will show some of those to verify that this is a reasonable approach. So for design purposes, optimizing the system, setting it up, these 189 rays were good enough. Once the system was optimized and we thought we have a good solution, we verified that with Monte Carlo's calculations, where you can now run as many as a computer can do, and these are millions of events. So the mass resolution. So in order to get a mass separation of 10 to minus 13, you need to separate the masses, and the question is how much? So if you look at the smallest mass difference, it's only 1/65 for the worst case, so the mass separation should only be 65. But we make if you make the mass separation only 65, then you don't take into account, as Manuel has already shown, talked about in his talk, you have a huge beam here and you have a very tiny beam here. So that is the difference. If you have two equal beam and recoils would be the same, the separation would not require much more than 65 and maybe twice of that, but it's not enough because you bury the tiny, I made this drawing here, here's a huge beam peak separated by d over sigma from the recoil, and you see here there's a tail. So we define the nominal beam rejection as the area, the area under this divided by the total beam. And this is the background from a Gaussian peak. Now, I call this nominal beam rejection because nobody thinks that in reality, up to d times sigma, the beam, or the recoils for that matter, would be Gaussian. So it's an artificial definition, and nobody really accepted that as a definition of what really happens. But it's still, for design purposes, a good tool. If I calculate this, I get a certain, I can specify numerically what the normal beam rejection is, and I can compare it with other systems. I can optimize it and see which elements bring this down, and then hopefully also the real beam with whatever tail there is, there may be background coming from other sources than just the beam, will also help achieve the design goal. So early in the justification why we take the mass separation of 750, as you know by now, the mass resolution, we had to take another approach. So what we know, we compared it with Dragon. We know that Dragon achieves a beam rejection of 10 to minus 13, shown by the experiments, with a mass resolution of about 350 for masses smaller than 30. So we thought at least for the masses 60, we need to achieve the same goal. So that would require, since we go to masses double the size, Dragon was designed only for masses about 30, but we want 60, we need roughly double of that. That were the number of 750, and that was considered in the reviews as a reasonable criterion to go ahead with the system here. But the nominal beam rejection I also used for optimizing designing the system. So this is ultimately the floor plan. You have already seen that most of the equipment is installed, except for the starting with the beam filter, not starting, but right now the beam filter magnet is installed, but not yet the electrostatic device. Beam filter 2 is not yet fabricated, still under production, but all the other elements, so the main thing of the footprint already there, installed, part of it commissioned. So you see here the target, the JINA-CEE target, starting with the quadrupole with the built-in hexapole. Then you have dipoles, and the first dispersive plane, focal plane 1, makes the charge separation, which is very important, as you know by now. The mass separation up to here is done with the first beam filter, and that is, the goal was 500, and then the second beam filter brings it up to 750. So this is now the full ion optics from the beginning to the system to the detector plane. And you see here the 189 characteristic rays. These rays are showing, we optimize the system with these rays, but of course if you have a specific question, what is the magnification doing and so on, in the last section I've shown you that you can do these calculations as shown there for St. George. You know now how to define a ray and eliminate all these and calculate then what a particular, the magnification does, what the dispersion does, and so on. So you know all to do that, how to probe the system. If you have a particular question, you take the COSI input of the last version, and then you just define a particular ray according to the definition, what you want to know. So here the total function of the system is characterized, is done in 4 sections. The first section here is up to the focal plane 1. Focal plane 1 after the 2 dipoles is dispersive, and the dispersion is good enough to separate, not separate, but select is the correct word, select one charge state. So starting from that, you cannot put any material anymore, because any degrader, foil, or whatever you would put in, or residual gas, possibly as a background, will give you, again, many charge states. So this is different from fragment separators, where you can put in a degrader or foil to make mass separation. Cannot do that here. Anything bothers. So everything has to be under high vacuum from here on. Of course, in the detector, you do then all kinds of things that you wouldn't be allowed here. So this here, focal plane 2, this is the second section, is designed to give the mass separation. So for the mass separation, you know how it's now defined, we need to minimize the size here, including the higher orders. And that size is then you divide the dispersion, mesh dispersion, divide by this number, and then you get the mesh separation. So in one VIN filter, we cannot get to 750 without making the VIN filter that we're building now is one of the biggest that was ever made. It's slightly bigger than what the manufacturer who did this has actually done. So we were comfortable that we don't have feasibility issues. But if you had one section, that would be so humongous that we had maybe instead of 300 plus minus 300 kilovolt plus minus 500 or 600 kilovolt, and that nobody has done, so we didn't want to make a feasibility study before we built the VIN filter. That's why we have two VIN filters for that reason alone. But there are other reasons to have several sections, because then you have in simulation shown that that helps to reduce the background. So several sections instead of one, like Emma, will help to get the background down. So that's why you have another justification for a second VIN filter. Everything you do in the design, and hopefully you can use, and later when you operate the system, has to be justified by the goal that you need to achieve. So there's a lot of thought going into the design here, as you can imagine. So then you have a second VIN filter section here. The first VIN filter section here is characterized, that's an achromatic focus. So that is to make it as small as possible. If it's not, the dispersion is large, then of course your incoming beam has a momentum energy spread, as you calculate in kinematics, and that spread would make that image large. It's a focus because you're not in focus. Also, this this image here will be large, so that's will require that. The achromaticity in terms of angular dispersion may not be an absolute requirement, but that will be, as you know, with dipoles here and dipoles. The first set of dipoles is here. The second set of dipoles is here. You can make this also dispersion zero, so the dispersion stays zero. The second point here is as a dispersion zero and the focus zero for the same reason, but not the angular dispersion. That could be done, but then you would need more magnets. This creates dispersion, these two dipoles. You would need another set of dipoles to counter that, as you know now from the previous talk. You need always two magnets to make it achromatic, coupled in a particular way by countering the dispersion from the first to the second. So if you run here the dispersion, then you would see here it goes to zero and stays at zero, but here it goes to zero, but it doesn't stay there. So that makes it a little bit more tricky to make sure that you have a small image here, but it saves here probably another set of dipoles. So these considerations went into there, and you know now what it does here. If the detector is not exactly here, but in front or behind it, then from the dispersion is no more zero, so you get an enlargement of the image. Of course, now you know you can all calculate that, and sometimes Fernando had a question, how accurate do I have to put the detector at that place before it starts to affect the mesh separation? And then I calculate and say a centimeter is good enough, or 10 is good enough, or you need to do it by a millimeter. You know now these sensitivity calculations, you can do that now. So if there's a question, ask the COSI setup. The last section is actually in the Dragon, not there. They separate the second section and there's no more, there's a detector right away. The simulation showed that this cleanup, that we don't want to put a detector here right away, but if we have a section where we can prepare the beam for optimizing adjustment to the detector, it also helps to reduce the background. So we call it cleanup section, but it's not only a cleanup section, But with particularly with the last two quadrupoles here, you can adjust the size here to realistic detector sizes, and if that changes, you have some flexibility there. So a cleanup here, reducing background helps in the cleanup section, but also adjusting for the detector. The whole system is optimized to fourth order. So the fourth order, you know now, are included into the edges of the dipoles. That's also why we have always, one of the reasons we have always two dipoles, because then you have four edges. And you have a question? Yeah?
I have two questions. The first one in section 2, you have a mass resolution of 500 and it's an achromatic focus.
Okay.
But you could have found another optics that was like, for example, mass resolution of 1000, but it's not an achromatic focus.
Well, what Fernando has found, he's already playing with the latest version of COSI. What he has found that the mass separation can actually be increased if you do not focus here. Now, from the design, I thought this is optimal, but that may not be true. If you give up here the focus, if the mass separation, in terms of the definition, what the mass separation is, it becomes the M17 increases quicker than the size of the image from the focus. It increases quicker, then the optimum may be somewhere else. So I think that is ultimately what Fernando is asking, and that question is not answered. It's not designed for that purposes, but there may be something better than what we have now. Now that is for somebody's project. That's not how this is optimized. You had a second question?
Yeah, section 3, the R16. Why do you want the R16 to be 0?
R16. This is the same thing. You have here the incoming beam has a momentum spread because of the kinematics. You calculate that. So if the dispersion is not 0 here, then you have, of course, an enlargement due to the dispersion. So I optimized it by having a focus and having dispersion. You mentioned, point well taken, that may not be the optimum how we designed it, but then the instrument may actually have a better, if we have a better compromise there. But ultimately, it's the same reason here how I optimized it. And nobody complained up to that point that this is a reasonable approach, but the system, if it's built, you have an idea, you have now the tools to take the model and see if that idea is really true. It may come out after somebody ran now the different dispersions and calculate the mass separation, it is actually optimal. My feeling is it is, but I haven't done the exercise. That answers your question. Okay, focal plane 4. Okay, fourth order, all optimized to fourth order. Why? First of all, I calculated 5th, 6th, 7th, and maybe even higher orders. Even where ion optical people, they say, well, that may not be so realistic anymore running with COSI. But anyhow, up to fourth order, nothing is happening. So if I calculate the mass separation with fourth order, fifth order, sixth order, it doesn't change anymore. So that indicates the system is optimized up to fourth order. How we optimized it? Well, the first approach was to take the dipole edges, and we have lots of them, in each dipole entrance and exit. Some may be effective, some not. You can calculate where a higher order is better optimized it, but usually there's no space for correcting it often. But you find one dipole edge which really is good to optimize it. The problem with is, okay.
Oh, sorry. Yeah, no, I have a question for the optimization. When you say you go to higher orders,
yeah.
if it's still optimized at a low order, wouldn't that speak to like your aberrations and also the emittance of your beam then too? So if you have to use higher orders to get an optimized beam system, does that mean maybe you should try and restart at your source or your initial tuning?
No. Of course, if you take all the characteristic rays, the higher orders are mainly driven by the large sizes in these places where the beam is large. That has nothing to do with the incoming beam. The incoming beam is a different calculation if you want. This is for the recoil beam, and even if the beam would be emittance of the beam would be a little bit larger, that wouldn't change this. Okay.
Sure.
There was another question.
You're talking about optimizing dipole entrance angles,
Okay.
or the shape of the dipole entrance?
Good question. First, you calculate all this in first order. You don't worry about the higher orders. In first order, you get, of course, the resolving power, and that is not. Then you calculate in second order. So by that time, you have adjusted your quadrupoles, and that's why there are quadrupoles here. And you have also adjusted the edge angles. Of course, in the optimization process, what you do, you make the edge angles, you tell the manufacturer this angle or that angle, the same cost. But if you need a quadrupole, then he charges you for that quadrupole. And if you have space at all. So in first order, the edge angle is already done in first order. Now we have quadrupoles after you do not change the angle, of course, at the entrance, at the exit of the dipole, but you still have quadrupoles to adjust. That's why when you make your sensitivity study and you change the length of the quadrupole, you can see only with the quadrupole, which you can tune, you can correct for that. And that's the reason. So the edge angle is already fixed. Then you go to the second order, and then you find out if the entrance and exit shape of the the second order can be corrected by a hexapole component in the dipole. And if not, or you want some flexibility, you build in wherever you can a tunable hexapole. So like this, you go order by order and come up then with where I was discussing up to fourth order. There was something to correct, but not anymore at fifth order, sixth order, and higher order calculations. So up to fourth order. Fourth order, another question.
Yeah, going back to the question of the beam spot, what Casey asked, the high order correction. So you have, if for second, the high orders are important, but you assume that the beam is an ellipsoid. If the incoming beam is not an ellipsoid that has like these weird shapes or something, wouldn't the high orders will make it much worse then?
I think I didn't completely get that question. Can you rephrase that or repeat?
This is really with his question about the
yes.
If the incoming beam has like it's not an ellipsoid that has a different shape.
What you're saying is the effect of the higher orders on the incoming beam?
Yes, if the shape is different than the ellipsoid, wouldn't the high orders will make it much?
Okay, well, of course, let's say this here is calculation for the recoil particles. If you take now the beam, not shown is here the beam. I will show a little bit about the beam. The beam is, of course, subject to the higher orders also. You just have different rays, and if the beam would be as large as the recoils, it will have a significant effect on the beam. But the beam is usually much smaller. The emittance you give me is much smaller, so the higher orders are not that critical. But of course, also the smaller envelopes, if you want, are subject to the higher order effects, just in a lesser extent. What this design calculation shows, that even for the biggest envelope, for the biggest quadrupoles, dipoles and so on, the higher orders are manageable. If you have a smaller, so the mass separation of 750 is for the worst case where everything is large. energy. In kinematics, you would see that's usually not the case. So the system is always better than the 750, but even in the worst case, the design situation, these 189 rays, we can handle it. We can get the 750.
So then to paraphrase, you start with like the worst case scenario for your initial beam conditions. You don't start with like the best beam or what you assume the beam is most likely, like a nice Gaussian distribution.
Exactly.
You start with like, I'm assuming the worst and I can still get it through, I'm good to go.
And I can get the corrected, even if the moment energy spread is 3.1%. If you go back here, you will see that for the angle of where we need the largest angular acceptance, the energy spread is also large. So that case would not be much better than 750. But any other case, you know, you see here the recoils are much smaller. So there you have actually the expectation that the mesh separation is much better because the higher orders will become smaller because you're not going through the large envelope. Okay. Yeah, thank you for your question. So we optimize up to fourth order, and higher orders are not relevant. The fourth order, actually, we have no magnet to correct. So we depend that the fourth order is corrected by the shape, the fourth order shape of the dipoles. We have no instrument to correct that. So that's why the sensitivity calculation showed that even the fourth order is not that critical. But we can correct by one octupole, which is actually sitting here. You saw that yesterday after the Wien filter on the right side, there was a hexapole and then an octupole. There's one octupole in the system where we can flexibly correct for, even if the calculation wasn't correct compared to reality. We have 4 hexapoles. So the hexapole we found out needs a lot of flexibility, and in the design that was very helpful. Often the manufacturer came with a solution where the hexapole was marginally a little bit out of specs. Now we could have insisted, you get those specs, otherwise you don't ship it. But if we found out we can correct it with the hexapole, we didn't send him to that exercise. Though legally we would have the right, because we wanted a working system and not showing that the manufacturer is actually fulfilling a contract. We wanted the system so that it works. So we have the 4 hexapoles where often needed to correct things like that. Okay, so of course, first order we have quadrupoles. Second order we have 4 hexapoles, and we built the first quadrupole with the hexapole inside, because the hexapole at the beginning was very important. But if we had a quadrupole and a hexapole, we would have jeopardized the large acceptance and make the system longer. So we built a magnet, which was a little pain for commissioning, because now you not only have a quadrupole, but you have a hexapole coil. And in addition, that hexapole coil, as it is created, as it is built or designed, has a dipole component. You have to compensate that, otherwise you have some steering from there. So that was not easy to commission. It's a little bit complicated system, but very important for the overall performance. So hexapole and 1 octupole, and high orders we showed is not relevant. So it's an OV command. You just go through 1, 2, 3, 4. You optimize the system. You find where the sensitivity are, and then you show that higher than 4th order is not relevant. Okay. So charge state separation. The charge state separation happens here at the first 2 dipoles. The notations here are not for the paper. Of course, I had to write B1, B2, but for my internal, I didn't do that. And but this is dipole 1, dipole 2. Then here the Wien filter. Then here the focal plane 1. And we show here in calculations what the charge difference may be, 1/33 or 1/15, depending on which reaction you take. So the worst case is 1/33, meaning the arsenic is completely stripped, which is actually a worst case, which is not happening because it's not completely stripped. We would change another charge state. But you see here still for that, the separation is here very well done. If you want to know more concrete, you take an experiment, you take the charge state that you really have, you put it in your COSI file, and you can calculate that. From a design point of view, the worst case is possible, but for a particular reaction, you will now use the COSI code to do that for your particular reaction. That was one of the exercises. Pick a reaction and then study it. That will be later if you do an experiment or you help somebody do an experiment. That's now what you can do. Okay, so, but here's the worst case, still nice separation from all the recoils. They're coming through here with one charge state, but the charge state difference can be separated here. Of course, if you take the easy case, 1/15, the separation may already happen here. So that's why you have flexibly at all dipoles, you see these big access ports. They are very important. They're very important to adjust to a particular experiment. Since nobody knows which experiment you want to do, we at least wanted to give you enough ports to put it there where it's optimum for your experiment, which you may be doing. Okay, so flexibility built in to eliminate the beam here as much as possible with different charge states than you're considering. So there's another question solved here. In case of the oxygen alpha gamma reaction, the separation is actually mass separation, very good. So we were, Manuel one day was wondering and said, well, are we maybe hitting the electrodes or hitting some other elements? So the answer is here, we are not hitting the Wien filter here. Here's the size of the gap. We are not hitting with the, what is it? With the oxygen beam, we are not hitting here the wall. And we actually, I'm sure, we adjusted the octupole here, so that also we are not hitting the octupole, which is the next element we would hit. So questions like this, now you don't go to the instrument, you don't have the beam time, nobody gives it to you for these kind of trivial questions, which may ruin your experiment, but you have a realistic model now where all, come to that, where all what we know about the system is put in, and then you answer the question here with your code. So COSI is not only important in this setup for designing the system, and then you're left alone, but for all questions, for particular experiments, you can now ask. Okay? So, now, the situation is you have 10 to the 13 particle, and you don't want to have one bad event where your recoils are. That is not possible to calculate. Manuel has done simulations, and he found that with his computer, maybe a factor of 10 you could do with the supercomputer, but then you're still not there. So the situation is calculated for 45 million particles. You simulate them with the Monte Carlo approach. So you take the system and you put many arrays in there. It takes probably, I don't know, he's not here to ask, but it probably many nights of automatic calculation to get this distribution. The recoils are, of course, also simulated, but there are so few that even 1 million you will not have. But for the exercise, it shows that we have, for this reaction, which is considered one of the worst, for the mass separation, you need the best mass separation you can get. The separation in that case is 21 millimeter, and from that you do not have a single event there where you put the slit for your recoils of the beam. Now, this doesn't say much, because even if there would be one event in here, but if there would be one event in here, it would already be a catastrophe, because you don't have 10 to the 7, but you would have 10 to the 13 particles or so. So one event in this simulation would already mean you have here 1 million counts. 1 million counts would shut down the detector. So this only shows how far we can push the simulation, but ultimately we depend that the mass separation of 750 will, and the indication from what was done with Dragon, and we have actually, I think, done a better job to separate the beam, so we will be okay. At least the experts and the funding agency approve that, but it still means we cannot simulate then the mass separation. So we need to build that instrument. That was ultimately the recommendation. You need to build the instrument to show that this can be done, but it is a reasonable approach, and you will probably be okay. But nobody can nobody can actually simulate it to the full extent. No computing power available for that. Okay. Yeah, we're good. So the question was always, well, how do you compare to Dragon? So what I actually did, Dragon was very well documented. They have all the effective field lengths and so on online. So I took the Dragon system and I put in the same arrays, the same characteristic arrays in it, and we get the mass resolution, what they claim they have seen with our characteristic rays, which means as it compares with the SECAR, we are good. I actually looked at some of the hexapoles, and I found out I could easily get the resolution of 480, so better than what they measured, or better, so that there may actually be better tunes than they have, but at least we know we are better than, we are good for our 60 mass 60 separation as compared to Dragon. So this is a way how to compare two things at the footing of our method, with our method. Not that that is absolute correct number, but okay. So now to another question. We want to do the reaction in a gas jet. But if you don't know the reaction very well, we discussed that before, you take the extended target and then you may miss. So not at the energy, you're not doing the reaction at the energy where the reaction is, but slightly off and you don't see it. So that's why the extended target comes into play. In the extended target, you have, say, a 10 centimeter tube. You don't have a jet, which is limited to 2 or 3 millimeter in all directions, but it's 10 centimeter long. So even if not, the reaction doesn't happen in the center of that cell, it may still be within the energy loss and different energies along that 10 centimeter. Okay, so the extended target. Then the question is, of course, what is then the effect on the mass resolution? Because now you don't know where your target is. It may be 5 centimeter in front or 5 centimeter later. You will localize it with a gamma detector, but your mass separation will of course be affected. So I just changed the position of the target, didn't adjust for anything, which you still may be able to do, but since you don't know where the reaction is beforehand, you don't know what to correct it for. So what is the mass separation? And then I calculated here the mass separation at the point, at the time we calculated that, we had a solution for 860 with all the changes. It's now at closer to 750, but just relative, you see the mass separation plus minus 5 centimeter with Cauchy calculation still gives a good, reasonable mass separation. So if the reaction is by accident in the center, you get 750. It deteriorates if the reaction is actually what you want to know, plus minus, you still have a reasonable mass separation, but not as good as if it were in the center. Okay. So ion optics during the project execution. So the ion optics, now a little bit an overview, the function of the ion optics. Of course, you know, once we have the ion optics has to fulfill all the requirements of the science goal. We talked about that. The ion optics allowed us then to define and specify all the magnets, the sizes of it, the precision, and so on, in particular in view of the critical mass resolution. So that goes in the specifications report, which a manufacturer gets, and he can be held responsible for doing that. But as you know already, we always verified that that is the case because he went through 2 steps. The first step is he made field calculations and design calculations to show that all the quadrupoles are actually doing that, what we specified. After the construction, we didn't okay it, but we just said, well, we don't see any problem with that. After the construction, which they had field calculations that showed it's possible, there are still surprises because the material is slightly different, etc. But he made field maps. So then new numbers came in. So actually the shapes of the dipoles with the all calculated are in theory correct, measured are slightly different. So that is the next step where we went through, calculate that. After installation, there's still an uncertainty. You may put the element wrong. This is called the element alignment. So with the element alignment, we checked that they're good enough. So finally, after all these exercises, we think we have a realistic model, and you actually have now a copy of it, which includes already all these steps in the manufacturing process. Now, dipole, now I go into the specifications of the elements. A dipole 1 is, 8 are specified. All the radii are reasonable radii. The magnetic fields have to be in this range. The angle is between 22 to 55 in dipole 4 and 1, 2, 3, 4, 5, and 6. The gaps are all between 60 and 100 millimeter. The horizontal good field region. So I have a complete list at the end where every magnet is specified, but this is just to give you an overview. And nothing here is for an iron-dominated, water-cooled magnet surprise. The edge angles are in this range, also nothing unusual. They're all vertically focusing. That helps usually to reduce the energy range or the excitation range of the quadrupoles. B5 is vertically defocusing. So now comes the tolerances are also specified, and the homogeneity is 2 times 10 to minus 4 or 0.02% in the good field region. Good field region is there where the particles, characteristic rays, are actually going horizontally and vertically. The FTXT field lengths in the good field region should not vary more than 0.2 times 10 to minus 4. The effective field boundary of the magnets, you have know the definition from yesterday, 0.1 millimeter. That is very tough, and the manufacturer signed the contract, and then you realize it's not so easy. So what did they do? Did I show that on the next slide? Well, it comes in a minute. Here you see how we defined the edges. You have, in my answer a question somebody asked. So the MC command allows you to not only make sure that 10 to minus 4, you don't change it to 10 to minus 4 or whatever the radial dependence is, but also to define here the edges. They're specified in the list here. You see here the S parameters up to 4th order. They define the shape here at the entrance and exit. The manufacturer said by building it and mapping and then finding out slightly off to 0.1 millimeter and cutting it again, taking it out, cutting it again, possibly cutting too much, you cannot really add. What he did, he introduced here the finger probes. So these are like field clamps, but they are across the horizontal good field region, and you can change these without machining anything. So he modeled those in 3D opera calculations, and then later, guided by these calculations, he adjusted so that the field shape. Here you see the ideal field shape, and you see here the tolerance we specified is plus minus 0.1 millimeter, and whatever he did, ultimately with these probes, he showed that in the calculation, they are good enough to bring in the good field region here from, is it shown here, plus minus, for this dipole 1, plus minus 10 centimeter, he met the specifications. So that was in the design. Then he came with a measurement, and the measurement is slightly different for many, many reasons. And you actually see that at 15% excitation, so it depends, of course, on how strong you exercise the dipole. We specified it in the range from 15% to 100%. So he showed here that it's, for most of them, it's actually within the plus minus 1, but at the lowest end, it's slightly off here. So we did some calculations and accepted the magnet. You can do some more calculations, but we accepted that magnet as being good. So that was done for all the dipoles and all the edges. I'm not showing all of these exercises here, but that should be included in the cozy version of SECA that you have. And still get 750 mass separation. That is a critical parameter. The envelope isn't changing. Some people always ask, well, is the envelope, by these small changes, the envelope isn't changed. Not changed enough. So the quadrupoles are also specified. We need horizontally more, larger good field region than vertically. So that is shown schematically here. I talked about the quadrupole 1 having not only being a quadrupole, which is shown here, but also a hexapole and the undesirable dipole. So this is a little bit a piece of art. Shailandra Chauhan came up with this design and gave us the idea, but of course, physically this is a little bit different than the calculation. Q1, the quadrupole overall length is specified. The focusing strength is the gradient times the length. So that's why Tesla. That is important for the highest rigidities. The apertures are defined here as an example for the two quadrupoles. The pole tip strength, which you enter into cozy, is calculated here. We gave some estimates what we could do of the power, but the manufacturer has thumb rules to quickly calculate that. That isn't the problem. The homogeneity, maximum inhomogeneity is 0.2%. That is the change from the linear gradient. So near the pole tips, the gradient, as you know, in a symmetric magnet will drop a little bit. that shouldn't be within the good field region more than this number. This is what this number means. Quadrupoles. Yeah, the hexapoles also specified. They're relatively weak. They're actually the only air coil magnets. You see, there's no water connection. If I remember correctly, you can check it. But because they are relatively weak, for the quadrupoles, the dipoles to be all water cooled. So, yeah, they're specified here. The Octupole also specified here. Standard design air cooled are sufficient. We thought they have to be water cooled, but the manufacturers said we built them without water cooling, which is one complication less. Okay, tolerances and alignment. The tolerances are all listed here. The most critical is in the homogeneity in the good field region. So in radial direction, which you calculate with, you can enter into the, I think MS command and the MC command will do it. And also the edges have the 0.1 millimeter, it's just summarized here. The quadrupole, the homogeneity, the Wien filter specification. Now the Wien filter 2 times 10 to minus 4 for the quadrupole can be measured. For the electrode, you cannot measure. You know, you would have to bring into a field which has plus minus 300 kilovolt a charge somewhere, measure the forces on that charge, and then calculate what the field is. Nobody has done that ever, and so there's no way. But the good news is in magnets, because of ferromagnetic magnets, you have material properties. So that is bad to calculate. So the field map is the ultimate judge that that magnet is good enough what you want. For the electrostatic surface, that's not the case. There's no material involved. So the calculation is pretty good if you know the shape of the electrode. So we held the manufacturer responsible for a particular shape, not the electric field, which he cannot measure, and I don't know how to measure it. Maybe you don't know how to measure. So ultimately, it's a shape and the positioning and misalignment of the electrodes, but there's no flexibility, which leads us then to the at least one parameter, the effective field length with the field clamp. It can be changed for the magnetic field, not for the electric field. So, ion optical, the tolerance, of course, the power supplies are typically a factor of 10 better specified than what the field is. We don't want to have a magnet perfectly and then it jumps up and down because the power supply is doing its game. So, for the dipoles, they're specified to be of the order of 10 to minus 5, about a factor of better than what we specify in the hardware. 10 to minus 4 for the quadrupoles, but I'm not sure they actually, it's probably the same type. Current stability. For the Wien filter, also the high voltage, plus minus 10 kilowatt has to be specified. Alignment was verified. This year shows the alignment. I don't go into detail, but they aligned it and then they gave us parameters, offsets of the center of the quadrupoles and the orientation. The magnets are not perfectly orientated, so they have what's called a roll, yaw, rolling. It's if you're in an airplane, the wings go left or right, and that's called roll. If the airplane makes this, that's called yaw, and the pitch is up and down. So, and those parameters you can get into. I made here. You may have actually that in your code for dipole 1. You can incorporate them. I don't go into details here, but if you want to know, we can talk about this down. Here's an example how that is implemented, the misalignment in the Fox file for COSI. Specifications for the velocity filter is here. Good field region plus minus 10 between the electrodes. Vertical is relatively small. The field is also relatively small, luckily, because with a gap of 90 centimeter, the vertical gap of the horizontal, you have seen that piece, you only need a good field region just in the middle and relatively small. To make there a Tesla field, that would be a monster. So, but the field is not very strong. Basically limited what you can do with the electrode, because the row, the E row and the B row have to be equal. So since we cannot go to higher here, that makes a relatively small dipole field. Nevertheless, the magnet is very heavy, a lot of power, homogeneity. The electrodes here, the electrodes itself are a ton heavy, and it's all titanium. So this shows a cut through the electrode, not the final version, but just gives you an idea. The coils are here, then these shapes are very odd shapes, but the good field region is only here, 7 centimeter horizontally and 22 centimeter vertically. Electrodes in the middle are cut here. This here shows the end of the quadrupole, the Wien filter of the electrode and the Wien filter. You know already that I have an issue of making the E over B as good as possible. So the electrodes, this here is in vertical direction. So you have the vertical magnetic field from pole to down pole, which is not shown, and in horizontal direction, the electrodes are, the field is here, only one pole is shown. You see here the fanning out. When we specified, we made first simple calculations like this in 2D, just to make sure we're not specifying something which is not possible, but the 3D calculation, optimization, 3D calculation were done by the manufacturer. MSU has the capability and people who know how to can do these calculations, but they're all busy with, with FRIP. So that's why we said we need a manufacturer who can do that. And they did. You see the field clamp here. The field clamp changes the effective field boundary. There's also a magnetic. There's also a magnetic plate here, and an electrostatic mirror plate, we call that, to shape the fields. Our calculation showed that we can do this E over B 1, so that the change from up to the good effective field boundary, where the field has dropped to roughly 50%, you have only a couple of percent deviation from E over B, which was considered acceptable. Yeah. Now, you're ahead of me because you have already seen that this system, which is photographed here at Danphysik, is actually sitting here. The Fernando and whoever helps him have already installed that here. As you can see, you see here the size of the whole thing. You see at the manufacturer, they tested it of all before shipping. There's a coil here, the lower part of the pole piece. I think the pole piece not yet put in. The sides, here the breakthrough for the chamber. Here they installed the field clamp. So the field clamp looks like this, and it will be on rails so that you can adjust it. The inside is not yet put in here. From this photo, this is the marvel of the electrodes. So it fits into the Wien filter. There are the two electrodes are here, very shiny for electrostatic purposes, and they are mounted here on ceramic standoffs. Here, the electric feed of the plus minus 300 kilovolts is not shown, not here installed at this point. You see here these little rings. There's an issue with what is called the triple bond. So where you have a vacuum, ceramic, and metal joining, the field can be humongous if you don't do that. So at this point, you need to shield from as much field as you can, and they're shielded by these called corona rings. So there's a lot of high voltage engineering going into this. I'm not going into that here, just that you know. We were collaborating with Sid Kreitzman from Triumph, who built similar devices. So, and Danphysik, our manufacturer, has actually done that job for them. So we knew they knew how to handle that. So all kinds of things. So if something else you don't know, you need to talk to the people who do and work with them. This is the message from this year. Okay, so this is here the next step. It includes now the installation of the power supply. So this beast here is from a company in Germany. They make power supplies up to 300 kilovolts, not an electrostatic device like you see in museums, but all built into a chassis like this, up to 300. Beyond that, you are a little bit on your own what you do, but this you can buy commercially. This is a cable. We try to make the cable as short as possible, because if something sparks, all the energy that is stored in a long cable would dump in your electrode. So that was a consideration here. You see here the vacuum pump, but you don't see the inside. I'm not sure. Isn't this already the electrode inside the high voltage vacuum chamber? Yeah, probably, because here's the connection. They actually commissioned the Wien filter with everything included, because the magnetic field doing commissioning without field is even a different game than with field. Because if you have a magnetic field, the electrodes that go there around, they will spiral, so they will do different things. So commissioning with or without field is one of the issues. Okay, this shows the effect of the field clamp. You can, of course, to make it even more complicated, the electric field length of the electrode will not change with excitation. It's given by the shape. But the magnet, of course, as we know, the effective field length changes. So at least we cannot change the shape very much, but at least we can reduce or increase the effective field. And these are the measurements that in the full range we can adjust it. We can adjust it by moving the clamp in and out to be exactly that what the electrode has, back to normal. So that is shown here. You see here in the vertical cut in the middle of the plane, you see here the electrode with the noses, nicely designed. Here is the mirror plate, electrostatic mirror plate. Hexapole and Octupole here. And I think this is my summary. The ion optical model has been used during the design, the construction, the measurement, and alignment phase of the project to update the measured electric field, higher orders, tolerances, alignment, to verify the system performance. So you have a calculation that includes all, if not most of it, if not all of it. This process is complete except for the Wien filters. They're still under construction. The commissioning and the conditioning of the electrode, that means bringing them to full voltage, has been a little bit painful process for Wien filter 1. It's now coming, but Wien filter 2 is still out there. The updated ion optical model will be used in the commissioning. Already Fernando is asking here questions, giving me sleepless nights. No, I'm just kidding. Operation and explanation where all measured parameters are included. So, and then this slide I showed at the last review. The funding agency wants to hear from time to time that we are on track with the manufacturing and that we are ready to use the instrument. And I hope this lecture has helped to bring up the expertise of more of just a few people who have been working on it now, but other people who can help to operate the system, run it, do experiments, or help those who will do experiments. So this is the situation of SECA as of today, and we are chugging along. Okay, I think we are reasonably in time. He's ready for applause, but nobody there to encourage you. No problem.
So this is the end of the lecture part?
Yeah, questions? Yeah.
The SECA has mostly used the mass separation to reject the beam, but could it also have been using, for example, the energy separation?
The what? The
energy separation.
No. See, the energy is given by the momentum. So the energy, if you calculate the momentum, you will find out the recoils and the beam have basically the same momentum. There's only the gamma coming out, which interferes with the momentum very, very little. So if you make the rigidity or the momentum is almost the same, except for the different charge states, because you know the formula for the magnetic force. It is very different for it goes to the inverse of the charge. So the charge state can be separated, but not the recoils and the beam once you have selected one charge. There's only one way. Of course, if you would make time of flight, then you would, in the detector, we will be doing things like that. We can distinguish between beam and recoil. But if you just let the beam through and put a detector there, you have 10 to the 9, 10 to the 6, and more than 10 to the 6, you cannot even measure. So you need the separator to first get the beam down where you can actually measure and use the power of the detector to do additional cleanup.
So the as you show in previous slides, that the detector can give an extra 10 to the -4 rejection.
Yeah.
That comes the time of flight.
Well, that is time of flight, delta E, possibly position. So there's a set. I have not talked about it. Jeff Blackmon, he is from what is it?
Louisiana.
Which university?
Louisiana State.
Yeah, Louisiana University. He built a detector. He has built detectors before of that type. Very familiar with that. He said he designing those. So they are positioned. There are channel plates for the time, very fast timing. So there will be time of flight section at the end of the system, where if you ruin the particle, you're not ruining the mesh separation. So initially you cannot have any material in there, but at the end there's a set of detector system that will do that job. And he says, no problem.
I have a question.
Yeah.
The scheduled meeting in October would be more advanced than this school.
This is this meeting.
Oh, but
There's no additional meeting. It's this meeting. I just said this is a slide that I showed at the last review, which DOE and National Science Foundation, and we announced that we would bring up the expertise that we have people who can help us, because the design team is too small to do everything for the experiments.
okay.
So we are hoping that you all will help with.
We have more experts.
Yeah. So this is referring to this meeting.
Any more questions? Okay, let's thank George.